So we've been talking about mixtures of gases. This also has application in scuba diving. When a diver breathes compressed air is at a higher pressure. If the pressure of the air is higher, then the partial pressure of oxygen is also higher. And that can lead to elevated oxygen levels in your body tissues. Now, oxygen is necessary for survival, but too much oxygen can kill you, right? Anything is toxic if there's too much of it. So oxygen toxicity would happen at an oxygen level of above 1.4 atmospheres. That would be the partial pressure of oxygen, not the total pressure. So that's at one extreme, too much oxygen. The other extreme is hypoxia, and hypo means below. So hypoxia means not enough oxygen, and that would be at pressures that are too low, and so that's going to occur around 0.1 atmospheres partial pressure of oxygen. So when you breathe compressed air, not only do you get more oxygen, you also get more nitrogen. So here at the surface, here at the surface, total pressure of 1 atmosphere. Air is 78% nitrogen, so we're getting 78% of that total pressure, so 0.78 atmospheres of nitrogen. At 30 meters of depth, in order to be able to breathe, the pressure of the gas you're breathing, the air, has to be 4 atmospheres. Now the partial pressure from nitrogen is 78% of 4 atmospheres, or 3.12 atmospheres. That's a lot more nitrogen. That can cause something known as nitrogen narcosis, also known as rapture of the deep. It has symptoms similar to alcohol intoxication, and as you may know, people who are drunk have impaired judgment, right? So being 30 meters below the surface of the water and having impaired judgment doesn't sound like a good idea to me. So what do divers do to avoid those problems? They breathe something other than compressed air. One solution to this is a gas mixture called heliox, which is helium and oxygen. Now, breathing helium gives your voice a real high quality, but it's not going to be toxic as long as you have enough oxygen with it. So here we have a diver breathing a heliox mixture with an oxygen mole fraction of 0.05. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? This is the partial pressure of oxygen at normal atmospheric pressure. This is what we are used to, and we function very well at that level of oxygen. So here this heliox mixture has a mole fraction of 0.05. Well, let's write down these numbers that we got. So for mole fraction, we use chi. So this is the mole fraction of oxygen is 0.050. And then we're told that the total pressure is what we're trying to find. So P total is our question mark. And we want the partial pressure of oxygen, so the pressure of oxygen, to be 0.21 atmospheres. So the mole fraction is like a percentage divided by 100. So I think I mentioned the example of a kindergarten class. You've got 20 children and 75% boys. How do you figure out how many boys are in the class? Well, you take the percentage expressed as a fraction, 0.75, times the total, right? And that gives you 15 boys. This is the equivalent of the mole fraction. This is the equivalent of the total pressure. What if I want to find out how many children would have to be in the classroom for there to be 20 boys? Well, then I've got 0.75 times x equals 20 boys. Right? I rearrange to solve for x. That's the same thing we're doing up here. The book gave the equation the partial pressure is going to be the mole fraction times the total pressure. So you can either think about how percentages work, or you can use the equation. It comes down to the same thing. So here, instead of solving for the partial pressure, we want the total pressure. So the total pressure is going to equal the partial pressure divided by the mole fraction. Just rearranging that equation. So I've got 0.21 atmospheres and dividing by 0.050. There's no units on that. 0.21 divided by 0.05, 4.2. So the partial pressure of this heliox mixture needs to be 4.2 in order for the diver to be getting the proper amount of oxygen. Any questions? When we have a reaction that gives off a gas as a product and we want to do something with that gas, we need to collect it. Collecting gases is a little trickier than collecting liquids or solids because they'll just escape, right? So we often collect gases by having them displace water from a container. I think I have a picture. There's the picture. So here's an illustration of collecting a gas over water. So we can start with this container. It looks like a tall beaker. We can start with that completely full of water, inverted in another container of water. And the water will stay in there because of the atmospheric pressure pushing down on the water out here. So that's going to stay full of water. Here we have a test tube. We're reacting zinc and hydrochloric acid, and that's going to make hydrogen gas. Instead of just letting the hydrogen gas escape from the test tube, we are going to contain it in this tube and direct it into this beaker. So if we are releasing the gas here inside the beaker, the gas is going to go up, and as it goes up, it's going to displace some of the water. So this is called collecting a gas over water. So we've got hydrogen gas in here, but this water is also going to evaporate, right? Because that's what water does. Water evaporates. So above the water, we're also going to have water vapor. So we're going to have a wet gas. We've got the hydrogen that we're collecting plus water vapor. And that's going to happen anytime you collect a gas over water. So we've got water vapor in the collected gas. The partial pressure of the water we refer to as the vapor pressure, and that only depends on the temperature of the water. Higher temperature, you're going to have more water vapor. Lower temperature, you're going to have less water vapor. And we'll learn more details about that later. To find the vapor pressure of water, we just look it up in a table, because other people have done the experiments and measured all of this. So this gives us temperatures at 5-degree intervals, and here is the partial pressure or the vapor pressure of water in millimeters of mercury. And starting at 0, it's very low, and as the temperature increases, it gets higher and higher and higher until it reaches atmospheric pressure at 100 degrees Celsius. There are tables available that have much smaller temperature divisions. This is not something you memorize, you just look it up when you need it. So let's do an example. A sample of acetylene is collected over water. The total gas pressure is 738 torr and the volume is 523 milliliters. At the temperature of the gas, 23 degrees Celsius, The vapor pressure of water is 21 torr. How many grams of acetylene are collected? Lots and lots of words. Let's pull out the numbers. So I have 738 torr. And what does it tell me that is? Total gas pressure is this. So we'll call that P total. Then we've got 523 milliliters, and that's the volume. The temperature is 23 degrees Celsius. And then we're told that the vapor pressure of water, so PH2O, is 21 torr. Now, if they didn't tell us the vapor pressure of the water, we'd have to go to the table and look it up. So I've labeled all my numbers. It's asking how many grams of acetylene, how many grams of the gas. Well, what can we calculate using the ideal gas law? Remember, we've got PV equals nRT. We've got pressure information. We've got volume. We have temperature. What could we calculate using this? Moles. If we had the moles of acetylene, could we calculate the grams of acetylene? Yeah. So what we want to do is we want to calculate the moles of acetylene. To do that, we want the pressure of the acetylene, the volume of the acetylene, the temperature of the acetylene. The volume and the temperature are the same for the water and the acetylene. This is a mixture of gases, water and acetylene. And so this total pressure equals the pressure of the acetylene, C2H2, plus the pressure of the water. Dalton's law of partial pressures. The total pressure of a gas is equal to the sum of the pressures of each gas. Well, I was given the pressure of water, so I can calculate the pressure of the acetylene. Pressure of the acetylene is going to equal the total pressure minus the pressure of the other gas. Here the math is so simple that it's difficult. It's the total minus one of the parts, and that's going to equal the other part. So the pressure of the acetylene is 717 torr. I see some concerned faces. Does anybody have a question? It's important to use the pressure of the gas I'm interested in. If I use the total pressure, I can calculate moles of gas, but it'll be moles of water and moles of acetylene, and that's not what I want. So there's my pressure. Is torr a good unit for the ideal gas law? No. We want to convert this to atmospheres. Conversion is 1 atmosphere over 760 torr. The torrs cancel out. How about this milliliters? Is that a good unit? No, we want it to be in what? Liters. Milliliter is a small unit. We're going to make the unit larger, so we make the number smaller. Milli means 10 to the minus 3. I'm going to remove the decimal point 3 places to the left. This temperature isn't good either. We need to add 273 to get to Kelvin. We got 296 Kelvin. Rearranging the ideal gas law, I get N equals PV over RT. So N equals PV over RT. We do this conversion to atmospheres a lot. And so one way you can shorten the stuff you have to write down is by just kind of combining this, we see that the torrs cancel out. I can just put 17 divided by 760 and the unit atmospheres. So 717 divided by 760 atmospheres. If you don't like that, if you want to just do the calculation and write the number in, that's fine. Why would I even want to do this? Because then I don't have to write down that intermediate value. I can just stick it in here like this. It's every time you write something down and punch it back into your calculator, you have two opportunities to make mistakes. So there's pressure, volume, 0.523 liters, divided by 0.08206 liter atmospheres per mole Kelvin, and the temperature in Kelvin. Again, be careful on your calculator because we're dividing by two numbers there. I'm doing 717 divided by 760 times 0.523 divided by 0.08206 divided by 296. I've got several numbers with 3 significant figures and one with 4. So this result would have 3 sig figs. This is moles of acetylene. So I need to convert it to grams. So I'm going to use the molar mass of acetylene, which I have to calculate. 2 times 12.01 plus 2 times 1.008. 26.036. So I do the math and I've run out of space, so I'm going to put the answer up here. 0.52886 or 0.529 grams of acetylene. Anybody else get that number too? Any questions? We're putting things together. So we've got individual skills here. We've got understanding partial pressures, calculating a partial pressure. We've got calculating moles using the ideal gas law. We have some unit conversions, and then we have changing moles into grams. Individual skills, we need to be able to put them together. Okay? Another example. Common way to make hydrogen gas in the laboratory is to place a metal such as zinc in hydrochloric acid. The hydrochloric acid reacts with the metal to produce hydrogen gas, which is then collected over water. Suppose a student carries out this reaction and collects a total of 154.4 milliliters of gas at a pressure of 742 millimeters of mercury and a temperature of 25 degrees Celsius. What mass of hydrogen gas in milligrams does the student collect? So, that 154.4 milliliters of gas, is that just hydrogen? No. It's hydrogen and water. Anytime a gas is collected over water, there is water vapor. They did not give us a partial pressure for the water vapor, the vapor pressure of water. So we need to look it up. So we need that temperature, 25 degrees. And we'll go back to that table. And here's 25 degrees. At that temperature, the vapor pressure of water is 23.78. So P H2O 23.78 millimeters of mercury. Now what's really fun is when the total pressure is given in a different unit than the partial pressure. That's always lovely. Well, okay, so we pulled that out. Let's get the numbers out of this equation. Here we have 154.4 milliliters. That's the volume. Pressure of 742. That's the total pressure. So P total had some technological glitch there, 742 millimeters of mercury. And the temperature is 25 degrees Celsius. Question?
Where did you get 23.78?
I got to 23.78 by going back a few slides and looking in that table of vapor pressures. Yeah, you gotta go look it up. Because sometimes you need to get things that are outside the problem. If that was an exam, probably on the same page as the periodic table, there'd be a table of vapor pressures. Okay, so I want the mass of hydrogen gas, but the ideal gas law doesn't allow me to calculate masses. It allows me to calculate moles, right? Where should I put this? I'll put this at the bottom, I guess. So we've used this bit rearrangement before. N equals PV over RT. When you have a mixture of gases and you're trying to calculate moles, it's very important to use the correct pressure. We don't want to use the total pressure. We want to use the pressure of the hydrogen gas. So the pressure of hydrogen gas is equal to the total pressure minus the pressure of the water. So that's going to be 742 minus 23.78. The calculator says 718.22. And that would be millimeters of mercury. Do you like the dividing by 760 in the equation, or do you like to do it separately? Doesn't matter? Okay, I'm just going to keep it in the equation then. So down here, we need the pressure of the gas we're interested in. So that's this amount in millimeters of mercury we need to convert to atmospheres. And the conversion is dividing by 760. So I can write 718.22 divided by 760. That converts it to atmospheres. And then I need the volume. Well, volume was given in milliliters, which happens a lot because that's a more common unit. So we have to convert that to liters. And if you're iffy on any of these unit conversions, you need to get some help with that. I can help you, or Chris can help you. Down here, dividing by R, 0.08206 liter atmospheres per mole Kelvin. And the temperature, and 25, not a Celsius, we can't do Celsius. 25 plus 273 is 298 Kelvin. So that's the temperature we want. So 718.22 divided by 760 times 0.1544 divided by 0.08206 divided by 298. 0.00 59668. Neglected to check out the units. Atmospheres cancel, liters cancels, kelvins cancel. I'm left with moles. So this is my moles of hydrogen. What does the problem ask me for? Milligrams, right? So I'm going to make some space up at the top because I ran out of room. So 0.00596668 moles of hydrogen. Before I can get to milligrams, I need to get to grams. So grams to moles, and then I convert to milligrams. So this is just straight out dimensional analysis. Okay, I'm back. So we need the molar mass of hydrogen. It's H2, so it's going to be 2.016. And here, a review of using prefixes. Milli means 10 to the minus 3. So I have milli on one side of the line. I put what it means on the other side. Milli means 10 to the minus 3. And so never put them together. 1 milligram is 1 times 10 to the minus 3rd grams. So I've got my moles, and I'm going to multiply by 2.016 and divide by 1 EE negative 3. And this is going to give me 12.029, which rounds to 12.0 grams. Anybody else? Sorry, not grams. What's the unit? I was like, that's an awful lot of grams. Milligrams of H2. Any questions? Again, combining several different things that we've learned separately. I guarantee there will be a problem on the exam that will require you to put things together like this in a way that we have not done in class.